This video is for the discussion of more questions on stoichiometry. Next, we'll discuss about concentration. So concentration usually will present it in moles in a dm cube. So if you have a dm cube of solvent, say water, and there is 1 mole of, say, NaCl that has been dissolved into this water. So we will get 1 mole in a dm cube of Na+, and we would also have 1 mole in this dm cube of Cl-. If I were to pour some of this solution into a smaller beaker, say this is just 50 centimeter cube. If I pour this solution in, it is still going to be 1 mole in a dm cube because I did not dilute the solution here. It's still the same solution. The concentration didn't change, but now there's less volume of it. So there would be less moles in this smaller beaker. The formula that we would usually use is mv/1000 equals to the number of moles. What is this mv/1000? M must be in mole per dm cube. V in your exam questions, it's often in cm cube, which is why I put the 1000 there. This is to change it to dm cube. Because M is in mole per dm cube. So if you have dm here, if you have mole per dm cube and dm cube here, you can cut it up, you'll get mole, just nice. Concentration can also be in gram per dm cube. That's just a different unit. So you can convert mole per dm cube to gram per dm cube, or from gram per dm cube to mole per dm cube. And the working for that is the same as when you convert mass to mole or mole to mass. So it involves the MR or AR. Okay, we can also call this mole per dm cube. Instead of calling it concentration, we can also call it molarity. This mole per dm cube is actually equivalent to this big M here. So 2 mole per dm cube of aqueous sodium hydroxide here is also 2M, that's the concentration unit of aqueous sodium hydroxide. So that M actually means molarity, which is a way to present concentration. Let's see, how do we prepare a solution which we want in a certain concentration. Lead nitrate solids was dissolved in water to produce a solution with a concentration of this. So we want the solution to have this concentration, 0.6 mole per dm cube. If 500 centimeter cube of this standard solution was prepared, so imagine this, we have a volumetric flask. A volumetric flask has cover like that, and a little mark that shows 500 centimeter cube. This was prepared. Calculate the mass that you need. So calculate the mass of this lead nitrate solids that you need. Let's ignore this. We're going to use the data booklet to be more precise to match the IB syllabus. Okay, so we have the M here, we have the V and per 1000. So then we can calculate the number of moles that we're going to dissolve into that 500 centimeter cubes of water. Okay, we'll start off with not 500, maybe less than that, say 250 of water. So this is just an estimate. Okay, MV per 1000, 0.6 times 500 per 1000. We will get, we'll get 0.3 moles. So we need to dissolve 0.3 moles into this water here, but that 0.3 moles, how are you gonna measure that in the lab? So we need to measure it by mass. So we can use a weighing balance. So to get the mass, use the MR here. Let's calculate the MR. PB is 207.20, N is 14.01, and O is 16. Let's go back to our main slide here. I got 331.22. Perhaps you might want to double check that. And 0.3 mole multiply this MR would give me 99.366 gram. This depends on how accurate or how precise is your weighing balance in school. How many DP will it give you? So you are to measure this mass and put it into this 250 centimeter cubes of water here, and stir it, try to dissolve it, and add washings from the container where you weigh this mass. Okay, after you see that it dissolved, pour this into the volumetric flask. So it won't reach 500, probably reach till this. Add more distilled water until it reaches that fine mark that you see on the volumetric flask. That marks 500 centimeter cubes. When you do that, and you need to invert and shake it to make sure the moles are everywhere. Okay, and when you've done that, then you would have gotten 500 centimeter cubes of a solution of lead nitrate that is 0.6 mole per dm cube. That is how you prepare a stock solution in the lab. Next, empirical formula and molecular formula. Empirical formula is the simplest formula. So for example, if I have butane, C4, H10, the empirical formula would be C2H5. Okay, if we do a question and we found this C2H5, they might give us the actual mass of that compound. And from this C2H5, we can get the molecular formula. Let's see the working. Questions might come in percentage by mass, or they might give you the actual mass. Either way, the working is exactly the same. So first we draw this table, the mass. So carbon, there's 85.72 grams. Hydrogen, there's 14.28 grams. I'm gonna get the AR from the periodic table. Carbon, 12.01. Hydrogen is 1.01. Therefore, the moles that are present is 7.137 something something and 14.1386 blah blah blah. Okay, I'm going to divide the smaller number, the smaller figure here, which is 7.137 blah blah blah. So that's going to give me 1 here, and 14.1386 something something divide 7.13 whatever. I'll get 1.98 something, which I can round it off to 2. Now, if you get something like 1.6 or 1.7, don't round it off to 2. You need to multiply a number that makes it a whole number. But I got something really close to 2, like 1.99 or 1.98. So I know that this is CH2. You can try this on your own. Draw this type of table first and use these percentage as if they were mass. Use our own data booklet. Let's not use this. And your answer is gonna be K, ER, O3. Let's look at combustion. Later we'll use the combustion data, but let's analyze this organic compound first. I didn't use very precise figures. You can correct that with the data booklet. This is the gist of it. Okay, so in combustion analysis, all the carbons in the hydrocarbon or the organic compound, carbons will be converted to carbon dioxide, and all the hydrogen atoms will be converted to water. Okay, for example, 0.5 grams of an organic compound. So it says organic compound, it doesn't mean that it's a hydrocarbon. It might contain oxygen. So if it contains oxygen, then it's not a hydrocarbon. Okay, 0.5 gram of this organic compound, it produces 0.733 grams of carbon dioxide. So we can get the moles of carbon dioxide here. The moles of carbon dioxide, that would be the same moles of carbon. Okay, and there's 0.3 grams of water. That will be equivalent to half the moles of hydrogen atoms that is in this organic compound. Let's look at the working here. So mass over mR, that is the mole of carbon dioxide, which is the same moles as carbon. So I just multiply the AR of carbon. This will be my mass of carbon that is inside this organic compound X. Okay, same way. This is the mole of water. Water has 2 hydrogens in it. So multiply 2. Each of those hydrogen actually weighs 1.01, but I'm not being too precise here. So I got 0.033 grams of hydrogen atoms that is in this organic compound X. And the balance, so I have 0.5 grams of this compound X. I take away the carbons, take away the hydrogens, the leftover would be oxygen. Okay, now I can use the same method as we've been using all this while. Use this table to get the formula. So the mass, 0.2, 0.033, and 0.267. So the moles present, you will have to divide the AR. If I divide the smaller value, I'm going to get 1:2:1. So my empirical formula would be CH2O. The empirical mass would be, okay, I'll simplify it to 12 plus 2 times 1. Of course, you're going to use the more precise one, equals to 30. So that's my empirical mass. But it says that the molecular mass of this organic compound X is 60. So 60 divided 30, that's 2. So N is 2. I need to multiply 2, the whole thing. So my actual formula would be C2H4O2. Next, 20 centimeter cubes of a gaseous hydrocarbon. Okay, this time it's a hydrocarbon, so CXHY. Burn completely in oxygen, O2, to produce water and carbon dioxide. All of this measured in the same room. So 20 of that. And it produced 40 of this. Completely burned in exactly this much. Okay, so now they're all in volumes. Let's get it in moles first, in mole ratio at least. We know that volumes are going to divide 22.7. So all of this is going to divide 22.7. Or if you're using 24, all of this is going to divide 24. So it means that the volume ratio, it's exactly the mole ratio. Therefore, I can just get the ratio. I would have already gotten the mole ratios. So 20 is to 60 is to 40. That would be 1 is to 3 is to 2. Okay, we're going to analyze using this. 1 is to 3 is to 2. If one of these CXHY produces 2 moles of this CO2, it means that X here is 2. So there's 2 of that. Okay, let me draw that. So C2H, don't know. The Y is still unknown. Reacts with 3 of those O2. It produces 2 CO2. And we don't know how much of water. But let's balance this equation. Okay, if we have 1, 2, 3, 4 oxygen here, and 1, 2, 3, 4 oxygen here, where did this went? Must have been the water. So I should draw another water here. Right, so how many hydrogens are there here? 1, 2, 3, 4. Therefore, I know that this Y is 4. So I did this without the combustion data. You can just analyze this. So what is the formula of this hydrocarbon? It's C2H4. What is the balance equation? Oh, we already have it here. So C2H4 plus 3O2. You get 2 CO2 and 2 water. Let's try using this combustion data. This is true for all the hydrocarbons. So CXHY equals to, I should write this, X plus Y over 4. So not the whole X plus Y over 4, okay? So it's just the Y alone over 4. Oxygen, and X of carbon dioxide, and Y over 2 of water here. It's best that you remember this because it's not given in the data booklet. Let's try this. 10 centimeter cubes of this CXHY required 20 centimeter cubes of oxygen for complete combustion, and 10 of carbon dioxide was produced. Calculate the molecular formula of this hydrocarbon, all this under the same condition. They must always specify that it's under the same condition so that we can assume that this volume ratio is the molar ratio. So like I told you before, if you divide 22.7, all would have divided 22.7. If you were to divide 24, all of this would be 24 as well. In the end, you're going to get the same ratio. So that would be the mole ratio. We don't need to do that. So the mole ratio is now 1 is to 2 is to 1. Okay, this is X. So I would have already known X. X is 1. And here, 2 equals to Y, X plus Y over 4. So X plus Y over 4 is 2. And we've already gotten the answer for X from the ratio here. X is 1. 1 plus something equals to 2. 1 plus 1 is 2. So Y over 4 is 1. So Y is 4. So it's methane, it's a methane here. So I'm going to rewrite that as a methane. Okay, so I can complete this equation now, which would be 2 oxygen, 1 carbon dioxide, and Y over 2, 4 over 2, that's 2 water. Let me just jot this down here so that you can refer to it later. There you go. One last example, Cx HY plus X plus Y over 4 oxygen, X carbon dioxide plus Y over 2 water. 150 centimeter cubes of oxygen was added to, so we have 150 centimeter cube of oxygen, 20 centimeter cube of this hydrocarbon here. After explosion and cooling, the gaseous mixture occupied 130. What are gaseous here? Things that are gaseous here are oxygen and carbon dioxide. Under normal conditions, water should be liquid. So this is not a gas. So the total after the reaction is 130, this 130 consists of oxygen and carbon dioxide. Okay, but they remove the carbon dioxide by using KOH. Potassium hydroxide is a base and carbon dioxide is an acidic gas, so you can remove that. And after removing that, we find that there is 90 centimeter cubes of oxygen left overs. So out of that original 150 centimeter cubes of oxygen, 90 was left behind, as in like it's in excess, there's too much of oxygen, not all has reacted. So we actually only used 60 centimeter cubes. Okay, so out of all this 130, 90 was oxygen. So 130 minus 90 of oxygen, that makes 40 centimeter cubes of carbon dioxide. We have no information about water here, but that's fine. So 1 is to 3 is to 2. We're going to use the combustion data this time. Sorry, I'm going to erase all this, okay? Right, so X, we know that X is 2. So X plus Y over 4 equals to 3. And we know that X is 2. So 2 plus Y over 4 equals to 3. So Y equals to 4. So this hydrocarbon is C2H4.